Okay, next we'll move to the last presentation, and it will be given by Martin. And the presentation is about the comparing finite volume and finite elements for simulating laser shock peening. Please.
Okay, good morning, everyone. Yeah, I will just try if I'm able to. Yeah, good. So, hello, good morning. Yeah, I need to apologize myself because in this presentation there will be actually no fluids. So, sorry, no fluid structure interaction, but there is a lot of solids. So that's it. And let's hit some things with high power lasers just before lunch. So, first, this is an applied research, and it's driven by the efforts to improve surface properties of solid materials. So this is basically in well, steel and iron and stuff like that. If you create your part, it comprises material grains that when they cool, they actually shrink. So, and this generates close to the surface of your part, this generates some residual tension. And if you start to use the part, so you start to bend it and so on, the tension creates some crack initiation first, and then it promotes crack propagation. Here we deal with something which is called peening, and we basically hit the material surface to generate plastic deformation and to flatten and compress the material grains. And in the end, we want to have a residual compression in close to the surface, because this residual compression disallows for crack initiation. So that's the motivation in here. Basically, this peening stuff, well, it's rather well known, and first recorded occurrence was, I think, in 1908, where some welders in USA, they built dams, and they noticed that when they hit the new welds with hammer, the welds behave better. So this promoted generation of this hammer peening hammer, so they really hit everything with hammers. But then technology improved, and I think it was in the 1960s or 70s, something called shot peening appeared. So you did not hit the surface with a hammer, you hit it with a shotgun, basically, with a large amount of very hard balls, which generated the compression close to the surface. And now we are in 21st century, so we do not use shotguns anymore, we use high power lasers, because they are much more precise and they actually can induce much more energy than just the shotgun itself. So, but the hammer in here is slightly hidden. So where is it? So we have our target material, and here we have the material grains and the residual tension. We do not want this, so we, whoa, where should I point it? Oh, yeah. So we put a duct tape, basically some ablative coating on the material, then we hit it with laser, and the ablative coating, it's evaporated instantly and there is plasma generated. We need to confine the plasma energy close to the material surface, so we put water on top of it, and this is basically our hammer. So the expanding plasma is the hammer, and in our simulations, it's just a pressure boundary condition. So we have pressure which has order of magnitude of gigapascals, and the duration of this pressure pulse is in tens of nanoseconds. And we need to simulate the propagation of elastoplastic shock wave through the material, because this plasticizes the material and generates the surface compression that we want to have. So at the end we have residual compression or residual compressive stresses, and we are all good to go here. So that's it. So how do we simulate it? So now please finger crossed, because there is a video in here, yeah, and it's not working, sorry. So basically, this one should be a very nice video of plastic wave propagation through the material. Then here you see residual stresses, or well, after first propagation, then yeah, that it should be repeated the same way as it is done in the solver, because we use basically open foam solver for this dynamic loading, so where we explicitly simulate elastoplastodynamic wave propagation. Then this pressure boundary condition lives in tens of nanoseconds, but then we need to move the specimen to hit it at a different place, and there is basically 0.2 seconds for moving the specimen. So then we have static relaxation, because from the solid point of view, like point anything second, it's a static problem. So we do dynamic loading with elastoplastic wave propagation. Then we transfer the material state, which is this one is plastic deformation basically in the material, and we compute relaxation as elastic problem with prescribed material state, of course. And then we move the laser through Python. So basically everything is implemented as a combination of Python and OpenFOAM. So why do we even do finite volumes here? Well, we are at the OpenFOAM workshop, so we need to do finite volumes, but as Professor Jasák already said, like in solids, you usually do finite elements. But we chose finite volumes because this is a collaboration with industry, and we need to do something that is industrial applicable, and the problem has a high element of nonlinearity because of the elastoplastic shock wave. So yeah, because of the industrial application, our meshes may not be perfect, and if you deal with compressible flow and shock waves, or if you deal with any type of shock wave propagation, mesh sensitivity is a huge problem. So we do not need to have perfect meshes. Yeah, we have we need to have some kind of efficient parallelization, and everything needs to be open source because we cooperate with industry and we do not want to deal with licensing problems. So then, yeah, for wave propagation through, well, problematic meshes, finite volumes, well, we believe are better. We did some preliminary research in here, and yeah, then OpenFOAM is a cool software, so we did do it in OpenFOAM. Basically, yeah, the consequences, Philip Cardiff has usually a very nice lecture on finite elements versus finite volumes and solid mechanics, so I will just say that the problem with finite volumes and solid mechanics is that some informations are missing because of the different mesh connectivity. So I will leave it here and forward. And then from the point of view of governing equations, we do everything which is pretty standard. Here I need to mention solids for foam community because we basically took their solvers, put out everything that we did not need because we needed to make it fast or as fast as possible, and used it as it is. So in Philip's notation, this is a cell-centered finite volume formulation, which is pretty close to the original one, so published like 20 years later. So nothing new here. We use standard displacement formulation and yeah, small strains, so Hooke's law and stuff like that. Yeah, we did a little bit of programming ourselves, and it was caused by the fact that the dynamic wave propagation happens only very close to the material surface, but the relaxation, the residual stresses reach much more in depth of the material. So because of that, we need to have two domains, one that represents only the material surface, the other one that represents the full material that we need to simulate. And we implemented some way to directly map data between the meshes on the fly. So that was a little bit of technical programming in here. Yeah, some practical notes on using of these codes. So the problem here is a boundary condition, basically, because we have laser or plasma generation. So there should be, for completely physical model, we would need to have model for plasma generation, for transfer of energy from plasma to the material, and this we should not have pressure, but really like illumination of the material. And even the current literature on the topic is well, not convinced that these type of models really work. So we simplified it and we really start with just pressure boundary condition, but the downside is that it needs to be calibrated for any given laser, basically. So we have a spatial pressure distribution, temporal pressure distribution, and we need to tweak some parameters to get what we need there. And there is one more thing, and it's everything is pretty fast in the material, and we are interested in plasticization of the material, so we also need to calibrate our plasticity model in here. So that's for this in cooperation with well, another institute, we came up with some type of calibration experiments where we use as much of symmetry as we can. So these are circular spots, and this will be simulated as axisymmetric. But then this is close to the application where the individual shots of laser are overlaid. So we use this as calibration, this one as validation, and when need to calibrate our loading conditions, so our pressure, spatial and temporal distribution, and plasticity if required. Yeah, this is just experiment, just an example of how we do this. So the guys have the lasers, the guys have experimental apparatuses to measure it, and they measure residual stresses in the material. So they give us some points, and then we basically fit the points by our model in some way to calibrate it, and after calibration we test it on a pattern, and it should hit, well, it should predict at least qualitatively what's happening there. So that's it. Yeah, now for the plasticity. The first approach was to use something which is called von Mises, or ideal plasticity, where when we simulate solids and we want to have a plasticity, we basically add some maximal stress that the material is able to withhold before being permanently changed or plasticized. And this von Mises plasticity uses just constant criterion for the stress, for the equivalent stress that the material can survive. The problem with this model is that it's too simple in our case, because we have everything happens very fast, and the material properties are rate dependent. So we have we need to include some strain rate dependence, and for this the standard is Johnson-Cook model. So in here we have one constant material property. Here there are 5 constants, which is a little bit more complex to calibrate. The good news is that this model is standard, so there are standard calibration procedures using something called Hopkinson split bar. So you hit 2 bars together and calibrate response of your simulation, or Taylor anvil test. You basically point a gun at some anvil and once more calibrate the response of your material in your simulation. The problem is that the strain rate that you can get with these Taylor anvil tests is 10 to the power of 5 reciprocal seconds. In laser shock peening, the strain rates are 10 to the power of 7 or 8 reciprocal seconds. So we have standard calibration procedures, but any LLSP is outside. So we need to extrapolate by orders of magnitudes, which is problematic, and we are currently working on how to calibrate this properly for laser shock peening. But yeah, just to show you the, well, promoted comparison of finite volumes and finite elements. This one was about, or everything up to now was about using actually something, well, about actually using something in applications, but we wanted to also test how we compare with with what is available. And for that we found a very nice paper, quite recent, where they did a very simple laser shock peening of some cube or hexahedron with one shot, and they evaluated different spot sizes and stuff like that. And we, well, replicated in finite volumes. We used a different type of mesh, which, well, but yeah, otherwise everything is the same. So no calibration for loading, so because we took it from the paper, so this is pressure spatial distribution. This blue line is pressure temporal distribution. Material properties, everything was the same as in the paper. So these, we have the Johnson-Cook model, which you actually had to implement in OpenFOAM. So this one is available, but yeah, some material properties, stuff like that. And here on these plots we have on the surface of the material residual stresses, and inside the material, so through the center of the spot and inside of the material residual stresses. In the paper they had also some experimental data, and yeah, the dashed lines are the results of finite elements. Solid lines are results of our framework. Here on the surface, well, the magnitudes that we catch are, well, the same as in finite element. There's a little bit of difference at the site of the shot. We are not actually sure which one is closer to the reality because the experimental points are pretty far away. And in depth, yeah, everything agrees rather well, okay with the measured data, but I'm actually not sure why the evolution of the finite element simulation here is not a smooth curve, why it oscillates in this manner, because I do not see physical reason for it, but still, well, it's roughly the same. But the main reason why we chose this paper is because it's basically the only one that we were able to find that deals also with the dynamics. So these are qualitative results of the elastoplastodynamic wave shockwave propagation, and everything is the same scale. This one is finite element, it's abacus, so it's abacus explicit, implicit, for those who are versed in this. And this is our simulation. And the good news is that basically everything looks the same, which is okay. Now we see a difference, but yeah, if I go a little bit back and show you the meshes, here you can see transition from a very dense mesh to a coarse mesh. Yeah, in our simulation we have a smooth transition and a little bit more below. And the difference in the dynamic data happens directly at the transition. So I think that these results are actually filtered by mesh. There is some refracted wave because of the interface in the mesh, and this energy is filtered out, which is the cause of the difference in here. So this one is for the spot size of 3 millimeters, spot size of 4 millimeters, so different spot size. Everything is basically still the same. Yeah, our mesh is a little bit denser, so we catch some of stuff that there. I don't know if this is filtered out by post-processing or by the mesh itself, but yeah, we catch a little bit of these secondary waves in here. But on the other hand, these data seem to be more dispersive compared to the finite element simulation. But once more, I'm not sure about the post-processing, and these are cell-centered data as they come from ParaView, but if you use nice post-processing, you can hide the dispersivity in here if you want to. But yeah, same story once again, still everything is, even for different spot size. So, yeah, to be able to go for the lunch, now, first I need to thank the collaborators, because I said this is a collaboration between actually two research institutes and a company. And I guess, as you know, that once the company needs to be starts to be involved in something, it requires a lot of patience on their side. So I would like to thank them for this patience and for providing us with time and experimental data, and for actually taking the results of our simulation and trying to put them present them for the customers. Then there are quite a big group on the other research institute who provided with experimental data. So that's it here. At the moment, we believe that we are able to do these simulation of laser shock peening basically at the state-of-the-art level. Doesn't matter if you look at finite elements or finite volumes, this just work. We have this strain rate hardening through Johnson-Cook model, which is once more standard, but there is a problem with calibration. We are trying to push the state of the art with respect to this calibration at the moment, and also the lasers are not ideal, and we are currently developing some non-ideal loading for the lasers, but it's yeah, then yeah, there are some projects, but with this I would like to thank you for your attention. That's it.
Okay, time for discussion and questions, and okay.
Thanks for your presentation. I just have a very simple question for you that, in my opinion, you just finished a laser peening simulation for your project, but did you ever consider the phase change phenomenon in your simulation? Because I just checked the melting point of the aluminum alloy you used. The point is quite low, below than 500 Celsius, Kelvin. So I guess, because I don't know the power of your laser used in your experiment, so I'm not sure. But I guess if you add a phase change, physical modeling in your simulation can be much better to describe the phenomenon. Is that correct?
Okay, thank you for your question. And there was first the power of our lasers is in units of gigawatt per centimeter squared.
Okay.
So, but this power is actually so high that yeah, well, we do not have the presentation here anymore. But at the beginning, when I was talking about the physics of laser shock peening, I was saying that there is some ablative or sacrificial layer on top. And the way it works is basically the sacrificial layer is evaporated instantly. Okay, this one might. Okay, but it's yeah. So where I need to go? Yeah. The sacrificial layer is basically instantly evaporated, and there has been actually done even a research about how much thermal effects are important in laser shock peening. And the result is, okay, here. We have this ablative coating, and once you hit it with laser, this gets evaporated, basically, and partially converted to plasma. The heat effects in there are completely neglectable compared to mechanical effects. And there was actually quite a lot of research done in this area. So we do not need any phase change model because the phase change is so abrupt that it needs to be modeled. It's the conversion from plasma to pressure, basically, or from laser energy to pressure through plasma. If you do not include this layer, then it's the same story all over again, but you do not evaporate the coating. You evaporate the top part of your material. So the surface of your material is at the end burned, but once more, no modeling of phase change is required, truly, because it just it's conversion from laser intensity to pressure directly without the plasma.
Okay, thanks.
Thank you.
Okay,
Yeah, thank you for your presentation. I'm also interested in the FEM method, but I wondered how range is the strain range in this material.
In this, well, the strain rates in here are during the shockwave propagation. It's in aluminum, it's roughly 10 to the power of 7 reciprocal per second. If we use a different material like steel, it's 10 to the power of 8, usually.
Another question. Why are you using just Jones-Cook model? Yeah, because Jones-Cook model is old material model. So there's another material model like a modified Jones-Cook model. So yeah.
Yeah. We started by implementing Johnson-Cook because it's the standard. If if we look into the literature for simulations of laser shock peening and stuff like that, everybody does finite elements and Johnson-Cook. So this is why we started with it. We have also prepared implementation of this Lim-Hoch model from Professor Hoch from KAIST. And there is by people from our institute, there's simulation, laser shock peening, finite elements, and Lim-Hoch model. But we are currently just implementing it in finite volumes in our framework to be able to directly compare it. But yeah, there's problem with getting the calibration data. For Johnson-Cook and for lots of material, we have quite a plethora of calibration data. For any like modified, newer model, the calibration data database is much smaller. And before we finish our own calibration procedure, we are just sticking to the basics.
Thank you for your answer.
Okay. I think if there's no question, and I think let's stop here. And thanks again for the speaker. Okay, I make an announcement for the lunch. We the same way to the Peking University. And okay, let's stop here. Thanks all for your attending this morning session. Okay, thank you.